Before I get into the prepared remarks, I'd like to remind you that this is a basic course in design, and my topic tonight will be conducted at a very elementary level, and this is as it should be because of the difference of experience and knowledge of the group we have here. But also, we hope this will encourage you to ask questions in case there are some of the ideas or some thoughts that aren't clear to you, or if you'd like them expanded a little further. At one of the previous meetings of the class, you saw on the videotape pictures of various components of a substation and a very brief explanation of what their function was. And in designing a substation, you first have to establish on paper how these different components are fit together, how they will be arranged to meet the particular requirements of that project. In order to represent on paper these different components of porcelain and steel and copper and so on, standard symbols are used. These are standardized through the American Standard Association and other bodies of this type, and our company has its own particular set of standards that we use in our drafting procedures. And I suspect you'll hear more of this in a later meeting. The most basic drawing in designing a substation is called the single line diagram. This is the most simple graphic representation of a substation or any electric circuit. By definition, a single line diagram is a diagram which indicates by means of single lines and simplified symbols the component devices of an electric circuit or system and the general path of energy transfer. And that is, the one line diagram just shows the overall relationships between the components of a circuit and how energy is transferred through that circuit. After the one line diagram is drawn, more complicated drawings are developed showing more complete details of the electric circuits. This time I might pass these sketches out in place of written notes. I'll give you these sketches which you can use to take notes on, and I will be projecting these sketches on the screen, and we'll talk about each one of them very briefly. You might get the first sketch on. Each of these sketches is numbered, and we will refer to them by their number. There are a total of 7 sketches, so you should have sketches numbered 1 through 7. Sketch number 1 is an example of a very simple single line diagram, and this particular sketch shows details of the power circuit only. As you can see, we have shown the electrical relationships of the different components: disconnect switch, circuit breaker, disconnect switch, potential transformer, lightning arrestor. And you can see the path of energy transfer from the bus up here down through the disconnect switches, the circuit breaker, the other disconnect switch for the breaker, out onto the circuit. In this particular case, we've shown surge protection by a lightning arrestor and an auxiliary unit in the way of a potential transformer. We also have shown on this sketch the bushing current transformers on the circuit breaker. Sketch number 2 takes this same basic circuit, and we have expanded it to show the relationships of other electric circuits as well as the relationships of the various components in the power circuit and the components in the auxiliary circuits. We have shown now the secondary circuits of the bushing current transformers, two sets of bushing current transformers, and also the secondary circuits of the potential transformers. And we can see the relationships between the potentials and the currents and the relays and instruments which they serve. We have the path of current flow shown still in single line diagram and with simplified symbols of the current circuit from the secondary of the bushing current transformer through the protective relay, this being the phase relay, this being the ground relay, and here to ground. And here in the other circuit we show the path of current through the watt meter, through the var meter, the ammeter switch, and the ammeter, and then there are potential circuits to the watt var meters through an auxiliary polarizing transformer to the ground relay. We have taken then one of the secondary circuits and expanded it to show how it would be represented in the full line, or this could almost be a wiring diagram. This would be more commonly referred to as a three-line diagram. There is the metering current transformers, which were shown just as a single component on the one-line diagram. But since this is a three-phase circuit, we of course have three transformers, one on each of the bushings of the circuit breaker. There was some identification left off of this sketch, I see. This is the current elements of the watt meter. These are the current elements of the var meter. This is the current element in the ammeter. And this is the ammeter switch, which should be shown to show the current from one phase switched to go through the ammeter. So we can trace the path of current flow in this particular circuit, transformer down through the current element of the watt meter. We've shown here a two-element meter through the current element of the var meter. You note we come down here back through this path through the closed contact, through the ammeter, back around here through the other closed contact, and back this way, completing the circuit. So you have a complete electric circuit shown there. In this particular one, this one is not switched onto the ammeter, so you can follow the path through the elements of the watt and var meter, through this closed contact and back, making a complete current circuit there. Now we can show different electrical designs of substations very readily with our single line diagrams, since these are the simplest diagram that we can use to show the various components of an electric circuit. So we can refer to sketch number 1 again, which represents probably the simplest form of substation configuration, that being the single breaker, single bus, or the radial system. And here, for a given electric circuit, we have one set of isolating, interrupting, and protecting equipment. And as we've mentioned the functions of the different components previously and shown them in more detail. The next basic configuration is a ring bus. And you can see the ring bus, how it gets its name. It is a complete loop. It's a loop of different bus sections to which circuits are connected, and between the bus sections we have a circuit breaker or a transformer. That is between each element of the bus, a line or a transformer, we have a circuit breaker. The circuit breakers, of course, would be equipped with the various auxiliary devices as we showed on the more developed single line diagram, bushing current transformers. There would be lightning arresters and potential transformers also in this arrangement. However, just to show the basic bus configurations, we've eliminated all of the auxiliary equipment just to show the relationships of the circuit breakers and circuits. The path of energy transfer in this case could be flowing in the given circuit, could be flowing in both directions around the bus, out onto the transformers, out onto other transmission lines, could be flowing in on all lines and out on the transformers, any combination of energy transfer there. The ring bus still has a single circuit breaker per circuit. As you can count, the number of breakers is equal to the number of transformers and lines. However, no particular breaker is assigned solely to one circuit or transformer. This breaker is shared by this line and this transformer. So you have a single circuit breaker for each line or transformer, but it's a half of this one and half of this one. In relaying, we have to operate both of these breakers to disconnect or isolate this transformer. This gives you more flexibility than in the single breaker, single bus system, in that you can take any given circuit breaker out for maintenance or whatever purpose and still continue to carry load on all of the elements from the bus. With the previous sketch that we showed, the single breaker, single bus system, if you take the breaker out of service, then you've interrupted the circuit and cannot carry energy. This gets you additional flexibility with only a slightly greater cost than the other system, that you have the same number of breakers, which is the expensive element. You do add to the complexity of your auxiliary circuits in that you will have to parallel current circuits from breakers on either side of a line or transformer to perform your relaying and metering. The next, on sketch number 5, goes a step further. This would be the main and transfer bus arrangement. You have here the main bus, connected directly to the main bus, a circuit breaker feeding a particular line. We've shown two lines in this particular station. So it starts out in the same general configuration as your single breaker, single bus system. However, to get the additional flexibility of being able to do maintenance on a circuit breaker, we've added a bypass switch or a switch connecting to another bus, an auxiliary bus. This bus in turn is connected to the main bus through a circuit breaker. So it is possible to take this main line breaker out of service but still have this as your path of energy transfer. The two previous bus configurations that we have talked about, the radial scheme and the ring bus, are commonly used at Iowa, Illinois. Most of our 161 kV buses are of the ring bus type. Some of our 69 kV substations and 13 kV substations are basically the single breaker, single bus type. And we have had main and auxiliary bus, or main and transfer bus schemes in the past, and I can't think of any that are active right now, although there may be some of the older ones. We did previously have some of this design. Sketch number 6 then. Oops. This is another step in complexity. This is called the breaker and a half scheme. This particular configuration we are developing as the ultimate arrangement of some of our 345 kV substations under construction. We're also in the process of converting the 161 kV bus at substation 56 into this arrangement. In the breaker and a half scheme, you have two buses, and here again you will see this transformer or a circuit connected directly to one of the buses through a circuit breaker. Transformer in this case, this line in this case. And then there is a shared breaker between the adjacent circuits, the line and the transformer in this case. So you have the flexibility of being able to maintain any of the breakers without interrupting service, and you have, of course, then added the complexity of the having to relay or control these two breakers simultaneously to interrupt a fault in the transformer, for example. The two buses of the breaker and a half scheme are connected together by these loops. You might say that a breaker and a half scheme is a series of ring buses connected together. This, of course, is more expensive than the ring bus or any of the other schemes that we have looked at. We've added, of course, the expense of 1/2 a breaker for each circuit. We take up probably an equivalent amount of space that a ring bus does, but we do have another step up in reliability. With the ring bus, it is possible to have two breakers open at some time, which could divide your bus into two sections, which could be undesirable from a system operating standpoint at some times. The next one on sketch number 7 takes an additional step in adding components. This is the double breaker, double bus scheme. Have 2 buses, and any line or transformer is connected through individual circuit breakers to each of the buses. So you have complete backup, complete duplication of the facilities to feed any given circuit. We do not have in Iowa, Illinois, any buses of this design, or present time, as far as I know, are not contemplating any. This has been used in other companies, particularly in the extra high voltage area. This, of course, since you've duplicated everything, is more costly than any of the other schemes that we have talked about. Require more area, will require much more equipment, and your justification has to be on the additional reliability. If you want to flip the switch there, please, we'll take that slide off. With sufficient planning, you can develop from one scheme or arrangement to another. And I might use as an illustration of this, of how your single line diagram can change, the construction of our 345 kV bus at the Hills substation and how it grew. We started out we had 2 lines. That's not a very neat sketch. We had 2 lines, one going north to Minneapolis, this being the Minneapolis line, one going south to St. Louis, connected to a common bus, as you can see is your radial scheme, and we added in this case the 345 to 161 kV transformer at that point. If we had any problems in the transformer, we would have to open both of these circuit breakers. This particular device here is a load break switch capable of interrupting magnetizing current of the transformer or a certain amount of load current, so the transformer could be disconnected without interrupting our path through the bus onto the other transmission line. I made another mistake in that I drew my diagram too big. I'll have to start over to show how it grew. That's still legible. That's what we had started with. Then came the addition of the 345 kV line going west to Des Moines. And I'm going to draw this in the physical arrangement of this equipment for 2 reasons. It's easier for me to remember it that way, and also it almost has to be to see how this is going to grow. And you recognize that as a ring bus. kind of shaped like a pretzel, but we go from the St. Louis line through a breaker to a transformer. That's the shared breaker between those two. From the transformer, we go through another breaker to the north line up to Minneapolis, that being a shared breaker between those two. We go from that breaker around this loop, and let's see, oh, yeah, there's the line, around through this breaker, which is shared between the Des Moines and the Minneapolis lines, through this breaker, which is shared between the St. Louis and Des Moines lines, and we've completed our loop. So we do have a loop, but in a little different arrangement. The next step will be the addition of the line to our substation 56. We will still be a ring bus. We'll add a circuit breaker in here, and for convenience, we're putting the disconnect switch not immediately adjacent to the breaker, and our line to sub 56 will be out of here. Now I think you can start to see the breaker and a half scheme developing. We have a bus here. We have a bus here. We have a connection, this loop here, electrical connection here. And there is one bay of a breaker and a half scheme. By adding another breaker over here, we can have another breaker and a half bay. This will be really what is called a modified breaker and a half scheme, because the design of this particular bus ties the transformers directly to the bus sections through a interrupting device which can interrupt magnetizing current or a small amount of load current. But in the event of a failure of the transformer where it has to be relayed and you have to interrupt fault current, you would have to relay all of the breakers connected to that particular bus. It would take one bus out of service with the transformer. We're currently, I guess I mentioned, in the phase where we do not have the sub 56 line, where this breaker is not in place. We're operating with 3 lines and 1 transformer and 4 circuit breakers. Turning back to sketch number 1, since it's the simplest, one of the topics that was supposed to be covered in this particular session was substation components. And this part of the discussion will be very elementary, but perhaps you will think of some questions. This, we keep talking about a bus, which here is just a line. Physically, that would be tubing, cable, supported on insulators of some type. Could be bus bar, fully insulated, depending upon the type of substation. The next element in our path of energy transfer we talked about before is a disconnect switch. The disconnect switch is an isolating device. It is not capable of interrupting current, either load current or fault current, and it serves the particular function of isolating, in this case, the circuit breaker. It could be to isolate some other component of the substation. but as shown on our sketch here, it is used to isolate the circuit breaker from the energized high voltage circuits to permit work directly on the breaker. The oil circuit breaker then has the function of interruption. That is, it is the device that interrupts the flow of electricity on the circuit. It is designed to interrupt either the normal level of current that would be flowing to serve the designed load of the circuit, or in the event of an abnormal flow of current, such as would occur with a short circuit, it is capable of interrupting short circuit current within its particular rating. Each of these devices will be rated according to the voltage level at which they can operate and the current that they can carry continuously. In the case of the disconnect switches, the circuit breaker will be rated at a voltage rating. It will have a continuous current rating, and it will have an interrupting rating. That is the magnitude of the fault that it is capable of interrupting. The circuit breaker can be controlled in the manual mode, such as by an operator over the supervisory control system, or by a control switch in the substation, or it can be operated mechanically during maintenance. But for it's performing its normal function, it is operated either manually or automatically by action of the protective relays. The relays that we saw in the more complete circuit sense the flow of the abnormal current to the short circuit and call upon the circuit breaker to open its contacts to interrupt the current. As we saw in the sketch, which I can't find to project right now. There it is. Sketch number 2. We have the relay circuit, which we mentioned, which is fed by the bushing current transformers, and this bushing current transformer is a component of the circuit breaker. It is mounted on the bushings of the breaker, usually contained inside the tank of the breaker in the case of the oil breaker, and its particular function is to reduce the current that is flowing in the power circuit to a level that can be handled easily on your switchboards and in your circuits inside the control house. The magnitude of the normal current rating flowing through the breaker, 600 amps is a typical value. 1200 amperes is another standard oil circuit breaker rating. It would reduce then the current flowing in this secondary to 5 amperes, which makes it reasonable then to carry this current into the control building, onto control boards with which people will be working, and on which we would mount then the protective equipment or the metering equipment. This gives us then a quantity that we can easily handle. If we were to try and use the full 1200 amperes, this would increase the size and complexity of all of these devices. The potential transformers serve a similar function as far as voltage is concerned, their function is to reduce the voltage of the power circuit, which in our system can be in the order of 4,000 volts, can be 13,000 volts, 69,000, 161,000, or 345,000, and reduce it again to a workable level of approximately 120 volts. It would be 115 to 120 volts would be the equivalent voltage in the secondary, the potential transformer. The lightning arresters, represented by that symbol, have the function of diverting sudden transient voltages, such as are caused by lightning, to ground to protect the equipment within the substation, which could be damaged by this excessive voltage, and then to interrupt the 60 cycle current that will follow once the arc is established, permitting normal service to be reestablished. So we've talked about the relaying circuit. This is the metering circuit, and we take again these reduced levels of current and voltage to feed into these instruments. They are for the function of measuring the quantities that are flowing on the circuit, current, watts and VARs, in order to give us intelligence as to what is happening on the circuit. This permits an operator or someone to see what is going on out on the circuit. It enables us to determine what load levels are, what the extent of circuit loading is, and to plan for the future, as Harry Rood talked to you about.
Excuse me, I've got a question.
Yes.
Between your CO relay and your ground relay, what does that symbol stand for?
That's a symbol which I did not look up in our standards, but it's a convention which indicates that at this point you have the three-phase currents have joined. This is in the neutral circuit going to ground. We use it quite commonly on some of our drawings. I think it's one of our Illinois standard symbols, but unfortunately I didn't check our handbook of symbols before I brought the sketch here. But that's the point at which your phase currents join for the neutral return path. I think we're open to questions at this time.
Is sub 56 line going to be tied directly to the bus, or should there be another breaker?
Well, the circuit breakers for the sub 56 line, you see, what I have here right now is sort of a combination of the expanded breaker and a half scheme. Let me go back to exactly what we will have when the sub 56 line goes into service. Yeah, that's it. See?
Could you repeat the question so we can hear it?
Oh, the question was if the sub 56 line would be connected directly to a bus or if it would be connected through breakers. Is that correct? And it will be connected through breakers. This being a ring bus configuration, when the sub 56 line goes in service, you see it'll have a shared breaker with a Des Moines line on that side. It will have a shared breaker with the line to the north on that side. So there are the two breakers on the 56 line in the ring bus. Do we have any more questions? Well, I guess you know it all then, huh? I've done a good job.